All right, we're going to look at some closing questions for this chapter, chapter 6. What are discrete random variables? Well, a discrete random variable is a variable with a countable number of outcomes. Okay, so in the previous video, we looked at interviewing 5 people and counting the number of smokers. Well, that's a countable number of outcomes. It's somewhere between 0 and 5. Okay, so those are discrete random variables. The formula for expected value. Expected value in general is the sum of the probabilities times random variable. And if you want to go back and look at an earlier video on how that calculation actually works, you sure could. Standard deviation formula is this. The sum of the probabilities times x minus the expected value. I'm denoting it with x squared, or with x bar. Okay. How can we find the expected value, variance, and standard deviation if a random variable is transformed by, here's how I'm going to write this down. I'm going to write A, B, and C, just like this. Okay. And we'll put our answers there. So if we add or subtract something, what do we do to the expected value? Well, we do exactly what it said. We add, or subtract. I gave it the number k here. How does that change the variance and standard deviation? It doesn't. Nothing changes. They would remain the same. If you do a constant multiplier division, what happens to the expected value? Well, it gets multiplied by whatever that multiplier was. So does the standard deviation. However, the variance, and again, if you want to go back and look at this, we did an example where we actually calculated it. This gets multiplied by the multiplier squared. Okay? Because, of course, variance is the square of standard deviation. So it's transformed by the square of the transform. A linear transformation of ax plus b. Well, of course, the expected value would get multiplied by a, and then we would add b. The standard deviation would be multiplied by a, and that's it. The shift up b has nothing to do with it. And the variance will be shifted by multiplying by a squared. So a continuous random variable, this is with an infinite number of outcomes, or we sometimes just say uncountable number of outcomes. So how do we find the probabilities? We use the area of a density curve. Okay, and I've drawn just a very simple little curve here off to the side. So, for example, if I said, well, what's the probability according to the density curve that I fall between 0 and 1? You would come over and say, well, the area of each box is 0.1, so 0.1, 0.2, it's 0.25. And then I just remind you that if I change this problem to have those inequalities instead, that would not change the answer at all. And the reason is, if I say, well, what's the probability that x is equal to 1? That is 0. Because being equal to one outcome out of an infinite number of outcomes is really like saying a 1 out of infinity, it's approaching 0. Okay, so we use area. Of course, the most common we use is the normal curve. So, just a quick little review of typing things in. The law school aptitude test has a mean of 650 and standard deviation of 45. Only applicants over 700 are going to be considered for admission to a certain school. What's the probability they score over 700? So, we draw our curve. Remember, that's our work. So 650. 45, and we're interested in the percent over 700. Okay, so here I did put in my work from my calculator. Remember, you still go to that VARS, the second VARS, that distribution menu. You find normal CDF. It is cumulative. We're adding up a bunch of area. And then you do the lower bound and upper bound, so from 700 up, right? And then the mean and deviation, and there is our answer. Okay. Okay. Sam says he scored in the top 10% of people taking the LSAT. What was his score? So we draw our normal curve, normal setting, 650, 45. And I'm just going to put S here for Sam. So you have a choice here. He says he's in the top 10%, so you could put a little, arrow over with 0.1. I'm going to choose to do it this way and write 0.9 because our calculator always does area below. So I'm going to stay consistent with that. In this case, we use, in that same menu, that distribution menu, we use inverse norm. And the first thing we do is the area, and then the mean and deviation. And so, probably with scoring as it is, Sam's score was probably 708. What is it that makes something binomial? Well, there are three things that binomial and geometric distributions have in common. So I really want to focus on what makes it different, and that is that there's a set number of trials. Okay, it's always out of blank. But the other things that make it binomial, there are only two probabilities, success or failure. The probabilities are independent, so the probabilities don't ever change. Okay, but those things are in common with geometric. So how do you define a binomial random variable? Well, we start by saying x is the number of successes. I'm just going to put because you'd put it in context, number of heads out of 10 flips or number of whatever, number of successes out of n trials. And you'd add that again in context. And that is really what makes it binomial. The number of smokers we found out of 5. The formulas for expected value, it's just n times p. For standard deviation, it's the square root of n times p times its complement, and 1 minus p. Now, how do we use them? Well, we don't really use them a lot anymore. How we used to use them was we use the normal approximation to do kind of big mass calculations of binomial distributions. So for example, in the previous video, the example with the smokers, if instead of interviewing 5, I'd interviewed 1,000, I said, what's the probability between 200 and 400 said that they would say they were smokers? You would calculate the expected value and standard deviation and know that the binomial distribution approaches, it's very mound-shaped around its expected value, and it approaches the normal curve. So instead of, you'd put your expected value here, and you'd say it's normal with the expected value and standard deviation, you could then, what I said I think was 200 and 400, you could use the normal curve to do this. And back before we had the distribution menu in our calculator, it was easier to find these probabilities this way. Now we don't really do that because we have the ability to do massive calculations with that CDF that we didn't used to have. So what is it that makes something geometric? Well, we already began talking about the three things they have in common: success or failure. Trials are independent, so the probabilities don't change. So what makes something geometric as opposed to binomial is it's the number of trials until success is the variable of interest here. So how do we define a geometric random variable? Number of trials until success. And of course, you would add the context here. You'd say, number of people interviewed until we find a smoker. Number of flips until I get a heads or something like that. So, and the expected value formula is 1 over P, the probability.